Hello, I'm Jason. Welcome to this section of the chemistry tutor. We're going to continue working with redox reactions, learning how to balance them using the ion-electron method. And so what we're going to do is jump into another example here, continue to get your knowledge and your experience and your skills up there. And then as we march through more and more problems, we'll get into more and more complicated guys. And as you do these things, you'll see there's a method to it. And so the trick is just to get that method and get the hang of it so that you're not flailing around whenever you're on a test. So what if I have the reaction, aluminum plus copper ion, which has a charge of +2, and that's an aqueous solution. So let me write aqueous here. And what I get on the other side is aluminum ions in aqueous solution plus copper, which is a solid. So this is a chemical reaction, and this is a redox reaction, and you can tell it's a redox reaction because you have all these charges everywhere. I mean, the only way that you're going to get charges before and after is if you have electron transfer. And we talked about the fact that oxidation and reduction is basically electron transfer. So in this case, we have aluminum that loses 3 electrons, becomes an ion, and we have copper, which is an ion on this side, and it must be gaining some electrons to become a neutral atom on this side. But if you didn't know anything about redox, you would look at this and say, oh, it's balanced already. What's the problem? You've got 1 aluminum and 1 aluminum and 1 copper and 1 copper. I'm done. So a lot of students that look at this on tests and they get confused. They're like, what's the deal? Well, even though the elements appear to be balanced, there is electron transfer that's going on, and that's not balanced. So that means that these coefficients of 1 that are everywhere, they're not what's really going to happen, because the real stoichiometric coefficients that are really, that you would see if you measured this thing, they're going to be balanced based on the electron transfer and the mass balance of all the elements. So step 1, I don't know if you remember from last time, let me go ahead and write this down like this. Let's do step 1 is the half reactions. And when we write our half reactions down, we want to obviously have the electrons in there, but we want to also balance the elements. So when we write the half reactions down, we want to have the electrons in there, and we want to balance the actual elements that are there. So in this case, we have aluminum giving us aluminum plus 3 electrons. Now in this case, the element is balanced. The aluminum element is already balanced because it was actually already balanced up there. And the 3 electrons comes from the previous problem when we had 3 electrons there to give us this ion. Now let's look at the copper. We start with copper, right? And on the other side, we end up with copper. That's a solid, so it's a neutral guy. Now the elements are balanced. There's a 1 in front of each one of them, so that's already fine. So we have to be gaining 2 electrons. It's the only way that this ion is going to become neutral is if we gain 2 electrons. So when you're done with the first step of the half reaction, you need to make sure that the elements are balanced, okay? And you also need to make sure that you have the electrons in here. All right? So what we have in this situation is this top half reaction is telling us that it's losing 3 electrons. The bottom half reaction is telling us that it's gaining 2 electrons. Those are not balanced, and that is why this top reaction on the board, just with 1s everywhere, is not balanced, because there's electron transfer going on. So then we proceed to step number 2. So step number 2 is we have to balance the electron gain and loss. That's what we have to do. Balance the electron gain and loss. And so how we're going to do that is I'm going to switch colors, and I'm going to look. I have 3 electrons here and 2 electrons here. So I need to multiply these equations by something. So we'll do something very similar to what we did last time. I'll multiply the top equation by 2, and I've got Al yields aluminum plus 3 electrons. And when I do that, the equation that I get is going to be, actually before I write the new equation down, let me just write this guy here. The one underneath, I'm going to multiply by 3. Copper plus 2 electrons yields copper. Copper neutral, which is a copper atom. All right. Now the reason why I'm multiplying by 2 and 3 is because I'm trying to make 6 electrons here, and I'm trying to make 6 electrons here. You can use any numbers you want. It's just you have to make sure that when you do that, you're trying to get a number on the left and on the right, you want to choose the smallest numbers you can to balance the gain and the loss. And we'll get more experience with that as we do more problems. Now as we work on the top one, we have 2 aluminums giving 2 aluminum ions and then giving 6 electrons. All right? And then here we have 3 copper ions plus 2 times 3 is 6, and over here giving 3 copper atoms. So these are the 2 half reactions, and when you multiply like this half reaction really is equivalent to this one, and this one's equivalent to this one. They're just differ by a multiple. But now notice we have 6 electrons lost and 6 electrons gained, and as long as they match, that's all we care about. So what we do in the next step is, let me switch colors here. Step number 3, okay, we're going to add the half reactions. Okay, we're going to add the half reactions. So what you're going to get is add everything on the left and everything on the right. And so on the left we have 2 aluminums plus 3 copper ions plus 6 electrons. That's everything on the left. On the right we have 2 aluminum ions, 6 electrons from here, and then we have 3 coppers, which are copper atoms. Okay, and then what we do at the end of the day is after we add everything together, we see we have the same number of electrons on both sides of the equation, which is exactly what we want to have. When we see anything common to both sides, we can just strike through it because it's not really relevant in the final reaction. So what we have as a final answer is going to be 2 aluminums plus 3 copper 2 ions yields 2 aluminum with a positive 3 for those guys plus 3 copper neutral atoms. So 2 aluminums plus 3 copper ions yields 2 aluminum 3 plus 3 coppers, and this guy is the right thing. So if you really wanted to be explicit, you could go here and say, well, this is a solid, this is an aqueous solution, this is an aqueous solution, and this is a solid, because you know copper doesn't dissolve in water, aluminum doesn't dissolve in water, so the ions are dissociated in water. That's fine, but whenever you have the actual atoms, they're going to be solids, right? So this is what we have here. We have a situation with these redox reactions where we have electron transfer and then we have the mass of the atoms, or the number of atoms that we have to deal with. If you look at this reaction, it looks balanced to begin with, but you know it's not because you have these electrons that are transferred. If you do this reaction, you're going to see 2 moles of aluminum combined with 3 moles of these copper ions to give us 2 moles of aluminum ions plus 3 moles of copper ions. You're not going to see anything related to this up here, even though it looks balanced. So keep that in mind. You have to write the half reactions, then balance the electron transfer, then add them all back together and cancel the commonality. And if you've done it right, you should be canceling these electrons here. Now again, I'll reiterate something I said in the last section. This is still a fairly simple problem because there's no oxygens or hydrogens, and I can't show you until I get to a problem in the next section. But when you have hydrogens and oxygens hanging around in your reaction, it makes it even more complicated to balance. So what we've done so far is choose a couple of simpler problems to give you the basic idea. Okay, this is what we're doing. We're canceling electrons, we're making them all equal, and then we're adding them together. This process is basically going to be the same, but we'll add a few more steps to it in the next section to show you how to handle any type of redox reaction with electron transfer, even if it has oxygens and hydrogens, and even if it's a little more complicated to balance. So this is kind of like the skeleton of the method. In the next section, we'll learn the granddaddy full method, which is just all this stuff with a couple extra things. I wanted to ease you into it. So make sure you understand this, and then follow me on into the next section where we will outline and write down all of the steps needed to balance pretty much any redox reaction that you'll have in your class. It's bulletproof. It is kind of lengthy, but it is bulletproof. And once you get some practice with it, I think you'll find that you'll get the answer every time, and you'll feel confident, prepared for your quizzes and your exams.